Thank you. So I'm going to talk about the breaking of one RSB in the random regular Unsatisfied model. This is our work with Nike-san and Yumeng Zhang from Berkeley. So this is an instance of a random constraint satisfaction problem, or random CSP for short. So I'll start with a brief review. So in general, we have n discrete variables that are subject to n times alpha random constraints. Here, alpha is a constant independent of n, so this is a sparse hypergraph on the variables. And the general question that arises here is, what does the solution space typically look like? And this picture shows several phase transitions as alpha increases from the left to the right. These have been long conjectured by physicists and later proved rigorously in various models. This is the general picture that works for a wide class of models, including the random K-SAT or Unsatisfied, graph coloring, independent set, and a lot of others. So there's a huge body of work here, but I'm only going to point out two phase transitions that are going to be important for us: the satisfiability threshold, which is a constant density below which there is solution with high probability as n goes to infinity, and above which there is no solution. And another phase transition, the condensation threshold, which separates the satisfiable regime into two parts. Below this is the so-called replica symmetric phase, where the solution space has, in some sense, an unstructured geometry. And between alpha cond and alpha sat, it has a more structured geometry where most of the solutions are contained in a bounded number of clusters that are near or orthogonal to each other. So I'm not going to talk more about the satisfiable regime because our work concerns the unsatisfiable regime. So here there is no satisfying assignment, and we want to come up with an assignment that violates the least number of constraints. So more generally, we can define a random measure, mu beta, where beta is a positive constant, the inverse temperature, which is defined via the Hamiltonian hx, which is simply the count of the constraints violated by x. And this measure will put weight e to the minus beta times hx on assignment x. So it penalizes assignments that violate more constraints. And it's normalized to be a probability measure. So this is a random measure on the set of assignments. And as beta goes to infinity, this concentrates on the solutions when there are solutions and on the ground states or MAX-NAE-SAT configurations in the unsatisfiable regime. So the main question of this work is, what is the nature of the energy landscape as beta gets large in the unsatisfiable regime? Does this one RSB phase continue where we have the clustering of ground states, or something else happens? So to motivate this problem, I'll just mention two relevant questions from the algorithmic literature. If we define the ground state energy, E min, as the smallest possible fraction of violated constraints by any assignment, then a natural algorithmic question that arises is the strong gravitation problem, where we want to certify an algorithmic lower bound on the ground state energy, which is preferably close to the actual ground state energy with high probability on random instances. And there is evidence of an algorithmic threshold here at the density, which is polynomial in n. And another possible algorithmic question is to find an approximate ground state. There are quite a few recent works in this area that show that this problem is tractable when the density is large enough so that we are in the mean field or complete graph phase that has a conjectured FRSB structure. So the difference between these one RSB, one replica symmetry breaking, and full replica symmetry breaking phases is roughly that in one RSB we have a clustering of ground states, and in full RSB we have ground states that live in clusters within clusters and so on that are organized in an altimetric hierarchy of infinite depth. and there is a lack of separation between them. So this work will give a partial answer to this question, 1RSB versus full RSB, without addressing any of the algorithmic implications. So to be precise, I'll define our model. We worked on the random regular K-not-equal set because we assume, or it's supposedly technically the simplest of the several related models, K-SAT, random regular K-SAT, not-equal set, and so on. And so this is defined by having n constraints, alpha times n equals m, n variables, and alpha times n constraints. And it's a regular bipartite graph formed by them, which is sampled by the configuration model. So we assign b half-edges to all the variables and k half-edges to all the constraints and take a uniformly random matching. And we also assign a uniformly random plus-minus sign to all of the edges. And we say that a constraint A is violated. This psi A is the indicator of that if the variables contained in it combined with the edge literals next to them are all the same, so all plus or all minus. So for example, in this case, the blue edges are pluses, the orange edge is minus. The forbidden configuration is plus, minus, or minus, plus. So some earlier work about this model in particular are the following. First I'll point out a quick observation. If we take a uniformly random assignment, then the probability that a constraint will be violated is exactly 2 over 2 to the k. So it makes sense to relate the actual ground state energy to this probability. This is the expected fraction of violated constraints. And the work of Aklioptas, Nor, and Perez from around 10 years ago gave strong bounds on this fraction this worked well, but their margin of error is actually too large to distinguish the 1RSB and the full RSB phases. Another works recently are those of Sen and Panchenko that gave different bounds on this ratio that work well for large alpha, so in particular for alpha larger than 2 to the 6k. And their work shows that the ground state energy here is consistent with the mean field limit, which is conjectured to be full RSB. And also several other works that built on the much earlier work of Garnet from the 80s predict that there has to be a transition called the Garnet transition above the satisfiability threshold that separates the 1RSB phase from something else, which is not 1RSB. And the physicist's prediction in the 1RSB phase, this E1RSB, is predicted to give the actual ground state energy below alpha Gardner, and it breaks down above alpha Gardner, and we enter some different phase. To the best of our knowledge, there is no definitive consensus on the precise type of this phase above alpha Gardner. It could be 2RSB, full RSB, or maybe something else. And the contribution of our work is a proof that 1RSB indeed fails above this transition, this alpha Gardner, and we give an estimate of this transition. So precisely our result is that if in our model we take the expected difference between the ground state energy and the E1RSB, which is the 1RSB prediction coming from a variational formula, then in the limit, as n goes to infinity, this is non-negative, and it's strictly positive above this threshold, alpha GA, which is, well, we define it precisely, but for now, I'll just say that it's in the order of 4 to the k over k cubed. We have 2 technical conditions for this. The first of which we expect to be necessary, that k is large enough, bigger than some absolute constant. And our calculations only work for an alpha which is less than 4 to the k over k. So this range covers alpha Gardner, but not all alphas, but we actually expect it to be removed in the future. Actually, I just mentioned a similar result from recent years. Oeffinger, Chen, and Zhang showed that in the SK model, in 0 temperature, we have a full RSB phase by showing that the overlap distribution has infinite support, but actually on the sparse graphs that we are working with, the overlap distribution is not enough to characterize the behavior. So in the rest of the talk, I'll give a heuristic for the location of this Garnet transition. This side of the bound builds on the work of Kleopatra and Perez. So this is actually the much easier part of their work. This is a moment bound for the ground state energy from below. And so it's the following. The probability that the ground state energy is less than some epsilon is the probability that there is an assignment for which m epsilon minus Hamiltonian, so the number of the violated constraints, is non-negative. And this can be upper bounded by this formula here, which is the expected sum of contributions from the assignments. For x, the contribution is e to the y times m epsilon minus hx, where y is a non-negative parameter. And this is a reasonable upper bound since the contribution from the assignments that have ground state energy less than m epsilon is at least 1, and the contributions from the other assignments are less than 1. And this formula turns out to be an explicitly computable quantity, which is not very hard. So we can optimize it in y. And the optimizing y is this y star. It's in the order of root 2 over r, where r is the ratio of alpha and alpha sub. And this same quantity, so this optimizing y gives a bound, a lower bound on the ground state energy, above which this quantity is exponentially small. And that lower bound also involves this simple term. This calculation works in a regime that covers alpha Gardner, so we can start with this. But it turns out that this moment bound is not sharp. Why is it not sharp? Because let's assume it is. If it is sharp, then this quantity here is exponentially small, and the only contributions can come from the ground states, in particular from states that are locally optimal, in the sense that switching any variable to the opposite will only increase, so cannot decrease the number of violated constraints. And it turns out that in this y star penalized model, where y star is the one from above, there's actually a positive fraction of free variables. A free variable is one that can be flipped without increasing the number of violated constraints. So if we look at the variable v, then it has clauses next to it that are forcing it to take plus or minus, and that clauses that are not forcing it. And some clauses force it to be plus, some others to be minus. And the fraction of the ratio of free variables is the probability that this number of, among these number of forcing clauses, there are d clauses, and each of them is forcing with probability 4 over 2 to the k. About half of them are forcing it to be plus, and half of them are forcing it to be minus. So this binomial variable has to take the value half of its parameter, and it's a computable quantity. It turns out that there is a positive fraction of free variables, 1 over root d, fraction of them, which gives an exponentially large number of ground states, because we can flip each of them without increasing the violated constraint. Thank you. Continuing this observation, free variables might not be able to be switched independently of each other because they might be linked. They are linked, let's say this u and v of free variables, they are linked if they are contained in a same clause, and they can both take plus or minus, but once we flip one of them, the other will stop being free. This happens, for example, in this case, when all the other variables in that clause are forced to be plus, U and V can both be plus or minus, but not at the same time. They cannot be plus at the same time. If we take two free variables, well, from this picture, it follows that the approximate probability that they are linked is around 1 over 2 to the k minus 1. And using this, we can look at the free variables as the points in a branching tree or branching process that has the following rate. If we take a free variable and look at neighboring variables of neighboring clauses, then there are d minus 1 times k minus 1 of them. Each of these children is free approximately with this probability, 1 over root d. And each free child is linked to the original variable in the previous sense with approximately this probability. And the product of these gives the branching rate of this tree, which is in this order. And this, as alpha increases, this increases. And if alpha crosses this alpha Gardner, which is in the order of 4 to the k over k cubed, this quantity grows above 1. So then the free variables percolate. And this heuristic that showed the exponentially large number of ground state breaks down. So we enter some different phase in the geometry of the solution space. So this is the this is a heuristic for the approximate location of alpha Gardner. The exact formula is based on this idea, but it's given by a more complicated eigenvalue criterion of a so-called stability matrix that captures the effect of captured the spreading effect of changing a variable. And the actual proof is given by the application of an interpolation bound, which was originally given by Panchenko and Talleyrand and adapted to other models later. This gives the E1 RSB lower bound that we state to be the lower bound, and specific to RSB perturbation of this variation of formula gives a strictly stronger bound above this transition. So in conclusion, we showed that in this problem, the E1 RSB is a lower bound for the ground state energy, and so this improves the earlier result of Bakhlyaptas-Nora and Perez. And above this Garnet transition, there is a strictly stronger lower bound, so this 1 RSB heuristic fails. An obvious open question is the 1 RSB lower bound sharp below the Garnet transition? In principle, this should be doable by a second moment method, but this seems technically very challenging. And another open question, which is supposedly much more difficult, is what is the nature of the energy landscape above this Garnet transition? And also, does it have any interesting algorithmic implications? Thank you.